Chemistry Unit 30 Theory Video 6. Now we are going to learn about identifying OH or NH signals in an NMR spectrum. Now earlier we understood that OH would appear as a single peak without depending on how many H1 atoms or protons are there in the neighboring carbon group. So as a result, we can't identify whether it is whether it is something, whether it is OH or something else. And also we saw that in the OH the energy change range of chemical shift, we saw that it had or the ppm it had a big range. So as a result, there are a lot of overlaps that we might not be able to understand properly. The reason for such a single peak is because this H is getting replaced rapidly by other protons when there is water. So that proton exchanges very rapidly. Now here you can see CH3CH2OH. When there is HOH, H2O, it either it could be water or it could be acid. So this hydrogen will replace. Now as you can see here, it has been given in red and blue. The red one will be replaced by the blue of water, and they will be exchanged when it goes to the other side. So that reversible reaction will take place, and as a result there is one peak, right? Because there are many peaks. Now if ROH protons, the range of chemical shift is 0.5 to 6. That is huge. Then in phenols it is 4.5 to 7. Then carboxylic acids 9 to 13. Then amines 1 to 5. Then how are you going to figure out if it is 1 to 5, amines is 1 to 5 and alcohol 0.5 to 6? How are you going to identify which is which? So that is going to be a problem. So to that we have a technique to identify OH or NH. We can add deuterium oxide, D2O. If you add a small amount of D2O, what happens is the peaks will disappear. Peaks will disappear if it is if the OH and NH groups are there. So what happens is if there is OH plus D2O will give you OD, HOD, and that's it. NHCO, D2O, NDCO, HOD. So then what happens is the atoms of deuterium will not absorb the same region of electromagnetic spectrum. As a result, the OH-NH signal will disappear from the NMR spectrum. So then if you check against the peaks in the original spectrum, then you can say if it is whether OH or NH. Now we have identified that it could be NH or OH. After that we check with the data table, then we will be able to figure out whether it is NH or OH. So the OH and in OH and NH, the H1 atom is referred to as labile proton because of this reason. Write down a note on this. In the NMR spectrum, OH and NH cannot be identified specifically because it overlaps with other chemical shift ranges. Also, as it appears as a single peak because the rapid proton exchange when water or acid is present, it becomes difficult for us to understand which is which. Please write this equation down: CH3CH2OH plus H2O. So the H should be take different colored pens and write down this equation. After that, write down When interpreting NMR spectra, to identify OH or NH, we can add small amount of deuterium oxide, within brackets heavy water, which will exchange reversibly with the protons OH or NH, and write down this equation, these two equations. However, because deuterium does not absorb the same range of electromagnetic spectrum energy, OH and NH signal will disappear from the NMR spectrum. When the values are checked with the peaks and their corresponding energy values, we will be able to figure out if it is OH or NH. I hope you understood. If you have any questions, please ask. Before you go to the next part, please do question number 7. After doing the question, let's try to go to this carbon-13 NMR spectroscopy. So this is a new type of NMR spectroscopy that has been identified and has been used in medical diagnosis mostly. So here what happens is, in addition to proton NMR, carbon-13 NMR is also used by organic chemists. Now, most of the carbon atoms in organic compound are carbon-12 isotope. We know that. It has an even mass of carbon-12. So, as a result, it does not show any signal on the NMR spectrum, because we know that it shows only the odd numbers. That is, if it has an odd mass, such as 1H or carbon-13 only, it will show. 1% of the carbon atoms of any given sample will be carbon-13 isotope. Therefore, this carbon-13 will obviously show, will interact with the magnetic field and will be shown in NMR analysis. So, as a result, organic compound can produce NMR spectrum as well. Now, if there is a carbon-13 atom, then it will show a shift, and that collective shift is going to be shown like this. So that shift, the carbon-13 NMR will produce a spectrum with different chemical shifts for non-equivalent carbon atoms in a molecule. Non-equivalent means we are talking about the environment. Now, when you say the sp3 hybridization of carbon, the environment of carbon could be alkyl, then the CH3, CH2, CH. So carbon in the middle. So then, if there is such a value, then the chemical shift would be between 0 to 50. Then if it is next to an alkene or arene, then 25 to 50, like that. There is a range of values that would be given, chemical shift values that would be given. So just like the proton NMR, we analyze this carbon-13 and we match the different shifts to that particular environment. However, there is a little bit of a difference in here. The signals that would be produced in carbon-13 NMR will appear as vertical lines on the spectra. Then we don't have those complications that we had in proton splitting proton patterns. However, we need to understand that the number of carbon atoms might not and will not be proportional to the height of these lines. Now, when you take a chemical, if there are carbon joined with CH3, that doesn't mean the line for carbon CH is going to be 1/3 of CH3. It doesn't mean that they are not proportional, right? So now when you take the solvent that is used to prepare the samples for carbon 13 NMR analysis is CdCl3. So this will account for the small signal near 80 ppm that if we look at the graph, that will have to be ignored when we analyze this spectrum. So that is because of the C13 carbons in the solvent molecules. As you can see here, it is close to 80 ppm. This shift can be disregarded, but only that. I hope you understood. So here this carbon has two shifts here. For one, there are 3 carbons. However, for the middle carbon there are no hydrogens attached, so it will not be shown. Then CH3 would be shown. Only 2 peaks, one for the carbonyl group, that is C double bond O, and the other for the carbon atoms in the methyl group CH3. Even though there are 2 CH3 groups in the propanone, they are going to be equivalent. So as a result, because it is equivalent, they are going to appear as a single peak. What you need to understand is, I think I explained the hydrogen peak earlier. Please don't misunderstand this. In here, if these 3 are equivalent, if these 2 are equivalent, that is CH3 and CH3 are equivalent, then they will be shown as a single peak. But the carbonyl group, that is C double bond O group, will be shown as a different peak as well. So as a result, C double bond O will be shown, and CH3, there are 2 CH3s that will be shown as a single peak. I hope that that is something that you did not confuse. Now when you go to this, when you come to this chemical, C6H5CH2CH3, C6H5CH2CH3. So here what happens is, the carbon atoms in the benzene ring C6H5 they are going to be almost equivalent, but it will be affected there will be some slight differences because of the ethyl group in the molecule. So there is a cluster of lines between 130 to 120. So that would be if there is a slight difference. If they are completely equal like CH3, then it would be single line. But if it is not, then there would be some interferences. Write down. Carbon 13 NMR spectroscopy. In C13 spectroscopy, just like in H1 spectroscopy, a chemical shift is obtained which should be compared with the TMS peak and the chemical is identified. It will produce a spectrum with different chemical shifts for non-equivalent carbon atoms. That is, if carbon atoms are there with equal environments, they will be shown as a single line. Please draw this figure 30.22, then you will understand it better. As shown below in ethyl benzene C6H5CH2CH3, there is a cluster of lines between 130 to 120 because the carbon atoms in the benzene ring are, even though almost equivalent, have slightly different changes because of the ethyl group in the molecule. Right, I hope you understood. If you have any questions, please ask. If I did not, you might have got confused with some of the things that I have said, but if you did not get confused, then please proceed to the end of chapter questions. But if you got confused, please let me know. Then I will explain it further.